Basically, it's related to these two manuscripts. So in the first one, we have introduced the idea of numerical smoothing along with regularity analysis and how to combine with adaptive sparse grids and quasi-Monte Carlo with the main application of option pricing. And in the second paper, we have extended this to the context of multi-level Monte Carlo, and we add the application of density estimation. So my talk today will be structured as follows. So first, I will try to motivate the problem and give the framework that we consider. Then I will explain the numerical smoothing idea that we introduced. Later, I will state the smoothness theorem along with the related details and show how to combine the numerical smoothing with the different methods that we consider. And before concluding, I will show numerical experiments highlighting the advantages of our approaches. Okay, as some of you may know, I mean, option pricing are high-dimensional, non-smooth numerical integration or expectation problems. And the high dimensionality basically comes from three sources, either from the time discretization of a certain SDE that describes the dynamics of the underlying, or because you are considering multi-asset options with large number of underlying assets, or because you have your payoff, it's depending on the path, the whole trajectory of the underlying. For instance, you can consider the Asian type options. Also, usually the payoffs that are considered option pricing are non-smooth. For instance, you can think about the example of calls or digital options. And to the methods that are usually used to approximate, I mean, the expectation or the integration problem of interest can be divided into subclasses. So the first one are the so-called deterministic quadrature methods. And there you find the quasi-Monte Carlo quadrature methods, in particular sparse grids quadrature. And this type of methods really rely on the regularity and the dimension of the problem. So they critically depend on that. Now, on the other hand, the second class is Monte Carlo type methods. Although the standard Monte Carlo does not care about regularity and dimension in terms of convergence rates, the multi-level Monte Carlo does, as we will see later. And also this was also motivated by Abdu's talk, I mean, that smoothness impacts multi-level Monte Carlo. Okay, so the framework that we consider is the following. So we want to approximate a certain expectation of interest, where here the payoff is from RD to R, which is a composition of a non-smooth function with a smooth function phi. So there are three cases that we consider. So the first case where you have max kind of functions, and on that case, you can think about put or call payoffs. The second case is when you have indicator functions. In that case, you have digital option, barrier options, or also you can extend this to financial grids if you apply pathwise differential methods, or also distribution functions, something that is not related to finance, for instance. And the third application is if you have G is a composition of a Dirac delta function with the function phi. And in that case, you have the density estimation application, and also this can be extended to financial grids. Also, we consider the process here to be approximated by a certain discretization scheme. And for instance, here for illustration, we will consider the case of one or multi-dimensional geometric Brownian motion, and also multi-dimensional stochastic volatility models. For instance, the Heston model, where you have two SDEs, one describing the dynamics of the underlying asset, and the other one describing the dynamics of the variance of the underlying asset. Okay, now the question before introducing the numerical smoothing idea, how different methods are affected by the regularity. So let's start with quasi-Monte Carlo. So I will not talk too much here because Bruno has done a nice talk about quasi-Monte Carlo methods. But here I will specify that we consider rank 1 lattice rules that are defined, I mean, by the following estimator. And to be able to have error estimates, we consider the randomized version, so the randomly shifted lattice rule. So how quasi-Monte Carlo are affected by regularity? This goes back to the analysis of Niederreiter, who showed that the convergence rate of randomized quasi-Monte Carlo are of order of m to the power minus 1/2 minus delta, where delta lies between 0 and 1/2. And it's related to the regularity of the integrand G. And later on, a more deeper analysis was done by Sloan and his co-authors, where they showed that you can get the optimal convergence rate, which are for the O to the M to the power -1, if the integrand belongs to certain d-dimensional weighted Sobolev space with functions of square integrable mixed first derivatives, which are equipped with the following. Okay, the pointer. So with the following norm. Okay. So here we see first how the regularity affects the quasi-Monte Carlo performance. So if you get a nice property of mixed first differences, then you can get the optimal rates for quasi-Monte Carlo. Please feel free to interrupt me at any point in the talk if you have any questions. Okay, so the second method that we will consider in this work is adaptive sparse grids. So first, I mean, also this is can be related to Lorenzo talk, who spoke about MISC, which is a general version of adaptive sparse grid where you have the deterministic space and the stochastic space, but here we will only consider the integration with respect to stochastic parameters. So let's say that you have a certain d-dimensional function and the multi-index beta, and you want to approximate its expectation. So the naive approach is to apply the Cartesian quadrature operator. And then, as you know, this will be affected by what is called the curse of dimensionality. And then the idea is to come up with a better estimator in terms of constructing a certain set of indices, IL, such that you overcome that curse of dimensionality issue. And here one can write, I mean, the quadrature estimator as a sum of over a certain index set IL of mixed differences operators that are defined as tensor product of first order differences operator. And here I give you an example how this looks like when d equal to 2. So the main idea here is to come up with smart ways to construct this set of indices such that we have less and less the effect of dimension on the convergence rates of the quadrature. And there you find, I mean, different ways of constructing that set. One way is what is called the product approach, where you have the set given by the supremum norm of the index to be lower than a certain level L. A better way to come is a regular sparse grid or Smolyak kind of grids, where the indices are included such that the L1 norm of those indices are below a certain level. And in these two, the construction of the set is done a priori, okay? Let's say, a smarter way is to come with an adaptive fashion to construct that set. And in that case, the construction is done a posteriori. So this goes back to the work of Gersten and Griebel. And here you include the construction, as I said, in adaptive fashion, giving a certain profit thresholding rule. So you define what is called the profit. For instance, here you can define the profit as the ratio of the error contribution over the work contribution. So the error contribution basically measures how much the error decreases if you include the index beta to the current estimator. And the work contribution basically measures how much additional work you are penalized by adding that index to the current estimator, okay? And how it works basically, I mean, you start with a certain initial index and you look at its neighbors, and then you compute the profits of those neighbors, and you take the most profitable one, and then you repeat the procedure on the fly. So you do the same procedure until a certain stopping rule. All right? Okay, now the same question that we have posed for the quasi-Monte Carlo, how this affects the regularity affects the performance of adaptive sparse grids. So first, I want to relate, I mean, the performance of the product approach, which has been shown to have a convergence rate that is of order m here the number of quadrature points to the power minus r over d, where d here is the dimension of the problem and r is the order that the total derivatives are bounded, okay? And you see here that there is the effect, I mean, the exponential effect of the dimension that deteriorates the convergence of the quadrature. And this can be alleviated by considering adaptive sparse grids. And as it has been shown on these recent works by Shen and also Tamellini and their co-authors, and his co-authors, sorry, you can get a better rate that does not depend on the dimension of the problem, where here P can be intuitively thought about as the relation between the regularity of the integrand and the anisotropy that you have in the problem with respect to the different dimensions. And also, I should note that this is also related to the order of weighted mixed derivatives that you have bounded in your problems. Another thing is that this estimate is for unbounded quadrature. So if you have a bounded quadrature, also you can get something that is slightly different from this, but it has the same way of conversion that does not depend on the dimension. Okay. The third method that we consider is the multi-level Monte Carlo. I will not stop here too much because it has been introduced in many works, and the last talk also of Abdu was explaining this. So how the regularity affects the multi-level complexity. Also, this has been discussed by Abdu. So if you consider, so here we go back to the complexity theorem of the multi-level Monte Carlo method. And if you see, this is related to 3 parameters. The first parameter is what alpha, which describes the decay of the weak rate. The second parameter is beta, describes the decay of the variance, the speed of decay of the variance. And the third parameter gamma describes the growth, the work growth. And as you see, I mean, the optimal, you can get the optimal case, which is tall to the power -2, if you have beta strictly greater than gamma. On the other hand, you can get the worst case complexity if the variance decay is slower than the work growth. And as an example, I mean, if you consider the Euler-Maruyama case, then you have gamma equal to 1. And if you have G-Lipschitz, and given that you have a strong rate of order 1/2, then by Lipschicity, you can get that beta is equal to 1 equal to gamma. Otherwise, if it's not Lipschitz, sorry, the integrand, then you lose that and you will have the worst case complexity. I should note that you can use high order schemes like Milstein schemes, but this comes with penalties. So first, for moderate or high dimension, you can face coupling issues and also high computational cost due to the additional terms of the Milstein scheme compared to the Euler-Maruyama scheme. And secondly, there is a deterioration of the robustness of the multi-level, because on those cases, you will get a kurtosis that increases with the speed delta TL to the power -1/2 as delta T goes to 0. This is the mesh at each level of the multi-level Monte Carlo, compared to O of delta TL to the power -1/2 for Euler without smoothing. And you can get cases that are bounded, as we will show later. Now, since I spoke about robustness, let me explain what does it mean, the robustness of the context of multi-level. So if you consider the kurtosis, I mean, and it's defined as there. So the large kurtosis can be very problematic for multi-level Monte Carlo because it can induce an expensive cost to get reliable and trusted estimates of the sample statistics. Why is that? I mean, this can be seen by looking. Okay. So this can be seen by looking at the standard deviation of the sample variance. And you see that in order to control those estimates, you need to get a number of samples that is much greater than the kurtosis. And in that case, you have two issues. So if you have few samples than what is required, then you will not trust your estimates. And if you use more than enough samples, then this leads to high computationally expensive estimator. And why we require, I mean, the sample variance estimates, this is because the optimal number of samples in the multi-level setting involves, I mean, those estimates, okay? So there has been some successful techniques to improve the regularity for both deterministic quadrature and also multi-level Monte Carlo methods. For instance, in the context of quasi-Monte Carlo and adaptive sparse grids, there has been considered to use modification, so you convolute your integrand with a Gaussian kernel. Also, another way is to map the problem from the physical space to the frequency space, where you can get a better regularity. And this is something that we explored in a recent work with Christian, Antonis, Michael, and Raoul for living models, where then you can apply effectively quadrature in the Fourier space. I should note that this, I mean, kind of methods are subject to the fact that you have the access to the Fourier transform of the density function or the characteristic function, and they are cheap to compute. Another way is the bias-free modification, and this is basically goes back to the idea of the work of Romano and Tuzzi, where here you can get an expectation of a more regular object, which is here Black-Scholes price by integrating to a subset of random variables. Okay, we considered also this in the rough volatility context, and it was helpful for quadrature for the adaptive sparse grids and also quasi-Monte Carlo method. Now, in the context of the multi-level Monte Carlo, also there has been some ways to overcome the low regularity of the integrand or the quantity of interest. For instance, there were considered the implicit smoothing, where you use conditional expectation, but then it was combined with the Marstein scheme. Again, this is not always possible. There are cases, it's not trivial to which filtration or random variables that you can condition with to get better regularity. And also this comes with drawbacks of the Marstein scheme. A second option is to use regularization or parametric smoothing. However, one can see that, I mean, this kind of methods can have a problem with deterioration of the strong rate as the limiting case and additional bias that explodes with the dimension, that explodes exponentially even with the dimension. And we will come back to this point. Another way is to use the Malevin calculus. So you can split the payoff into two contributions, one that is smooth and the other it's discontinuous. And then you apply different techniques. For the smooth one, you apply the standard multi-level, and for the second one, you apply what is called the multi-level Monte Carlo method. And another way is to use adaptive sampling also. This can help. Okay. So now I introduce the idea of numerical smoothing. All right, so here we will use a guiding example to explain the idea. So let's consider the dimensional payoff G here. And we have X bar denotes the Euler approximation of a certain solution of this stochastic differential equation. Okay, so you can see the discretized path as a function of the delta W increments for each dimension, right? So the first idea of our numerical smoothing is to establish a hierarchical representation of those randomness. And what we mean here is that you can, so these delta W's basically are coming from standard normal random variables, right? And if you use, I mean, hierarchical representation or hierarchical construction of your Brownian motion, for instance, by using Brownian bridge or high wavelet construction, then you can get that the coarser random variables that are used at the coarser levels will contribute substantially, even if delta t goes to 0, and they contribute more than the other random variables in terms of the variance. So they have more information than the other random variables. I should emphasize that this way is totally different from previous techniques that they smooth out at the last step, but they smooth out with respect to delta W. And this can be problematic because the smoothing effect will scale with respect to delta t and it will vanish at the limit. Okay, so this is the first representation that we use. And on top of that, you can take the coarser random variables now Z1 and apply rotation to those random variables. This rotation usually depends on the structure of the payoff. So if you think about the basket option or arithmetic basket option, you can think about the matrix A having a row that is equal to the weights of those assets, and then use Gram-Schmidt to build the other components because they will not matter. And then you can get, I mean, the random vector here y that we will use for our purposes. All right, so we did two hierarchical representation. We started with how to construct the Brownian motion either by Brownian bridge or a higher wavelet. Then we also did the rotation for the coarsest variables, and then also intuitively we expect that the first variables of y, I mean, given they depend on the coarse level, will be getting the most important information. And here I will show the idea when we do the smoothing with respect to that direction. Okay, so initially we started with this expectation, and then you discretize your process. So you have the following quantity of interest. So this can be seen as a d times n dimensional integration problem. D is the number of assets, n is the number of time steps. What we do is that you do numerical pre-integration with respect to y1. So here I introduced this I, And I, as you see, is basically the integration of J here, capital J here with respect to the density of Y1. I should emphasize that J here basically it's kind of generic because you can see it as a composition of 3 maps. The first one maps your random variables to the Brownian bridge or Haar wavelet construction. The second map here gives you the time stepping, Euler, Maruyama, or whatever, and G is the payoff function. So this way is very generic. So you can apply it to different choices of discretization and methods to sample your Brownian motion. So now we had this we have this pre-integration with Y1, but remember that a lot of cases we don't know Y1. So what we do is that we try first to approximate this discontinuity location by Y1 bar, so we can use root finding method, sorry. This is basically related to this problem. So what we solve is that, I mean, coming back to the previous slides, I mean, the examples that we consider here, yeah. So the examples that we consider here, you can see easily that the discontinuity happens at phi of x equal to 0, right? So then to compute your, okay, so to compute your discontinuity location, basically you will get a problem where you try to solve for Y1 given the other random variables to be equal to 0. So this is what we solve with Newton or any root finding method. And also what we do is, I mean, given now we approximated the discontinuity location, remember that G here is expected to be smooth in the parts where we don't hit the discontinuity. So we try to separate the domain with respect to the discontinuity location. And then we have tried to approximate those integrals using two-sided Laguerre quadrature, for instance, okay? And what you end up with, basically, it will be an expectation now. I mean, you can see it as a d times n minus 1 integration problem or an expectation of this object that we called a bar. And we use the different methods that we discussed before, adaptive quadrature, quasi-Monte Carlo, or multi-level to approximate effectively these expectations. Any question about the idea of numerical smoothing? Okay, I hope it's clear. All right, so here I discussed that we have a single discontinuity, but we can also extend, I mean, if we satisfy some conditions, we can have problems where we have multiple discontinuities. This can be due to the payoff structure, or also if we will use Richardson extrapolation, as I will show later. And then if you assume that you have ordered multiple roots, then you can extend, I mean, the problem that we have before, I mean, this I that we have it here, but now you add the information of all the roots. So you have two problems that are semi-infinite integrals that are in the bound, that are in the extreme discontinuities, and then you have these integrals that for the discontinuities that are in between. And then what you do is that you use maybe Laguerre quadrature for these semi-infinite integrals, and you can use here for each one Legendre kind of quadrature to approximate them. I should note here that, I mean, you can approximate this further if you have some knowledge about the decay of the product of G times rho 1, because then, I mean, you can approximate, I mean, the semi-infinite integrals, or because you have some roots that are close to each other. So you can neglect, I mean, in a good way, I mean, these integrals that happens in between. Okay, so the second extension is how to extend this idea to the density estimation. So a density estimation, basically, you can see it as an expectation of a Dirac function, the Dirac delta function. So as it's known, without any smoothing, kind of regularization or kernel density, then Monte Carlo or multi-level Monte Carlo will fail because the singularity that happens on the Dirac delta function. This will induce infinite variance for your estimator. So what we do basically is that given the construction that we did, and if we condition with respect to the Brownian bridges that we have in our problem, then you end up with something nice, which is regularized, which is here equal to the expectation of something that kind of exponential with respect to Y1. Okay, multiplied by the derivative of y1 with respect to u. Here we try to solve, I mean, the location of the density here at the point u. Okay. Now, interesting question: why kernel density are bad? So, I mean, this is also was applied for the multi-level Monte Carlo setting. So this was related to the parametric regularization that was introduced by Giles and his co-author. The problem that this can have a bias that scales exponentially with respect to the dimension. I mean, this is you can see it from the standard analysis of kernel density estimator. So if you look at the mean square error, you will see that your bias here will explode with respect to the dimension of the problem. Okay. However, I mean, due to the conditioning with the Brownian bridge, and if we are able to compute, I mean, this continuity location, then we don't have, I mean, this dependence of our numerical smoothing with respect to the dimension of the problem, which can be very efficient in high dimensions. Okay, so now let's state, I mean, the smoothness theorem, which is the main contribution, I mean, that we have in this work, and this helped to construct effectively the different methods. So, and for that, I need to introduce some notations. So first, I introduce the notation of Haar basis functions, so which are constructed as such, where here psi is the Haar mother wavelet. Okay. Also, I define here the grid dn, basically, which is given by the following points, and you can observe that the Haar basis function at level n are basically piecewise constant with this continuity location that happens at the grid, at the points of the grid dn here. Okay, so given this construction of the Haar basis functions, you can have the antiderivatives of those bases, and then you are able to construct in a hierarchical way the standard Brownian motion. So here I show the truncated version of it. So here you can construct the truncated Brownian motion as a contribution that happens at the coarsest level in some sense for this antiderivative of the coarsest Haar basis, and you have this contribution that comes from the other terms. I also define, I mean, the increments of a process as we do here for the sake of notation. Yeah. And we consider the solution of the Euler scheme of this SD, okay? And then we write here how the discretization is written with respect to the level L. And here I need to define the important, I mean, function that we will do the analysis for it later, which is called Hn. So Hn can be seen as a deterministic function with respect to zeta n. So let me say that zeta n here corresponds to all random variables that were used except, so what we needed here, we use those random variables. So I'm calling zeta n the random variables that contribute for this term, except zeta minus 1. Okay, so you can see that the Euler discretization as a deterministic map. So given zeta minus 1 and zeta n, this is a deterministic map, right? And this is also applies for Hn. So if you take it as the expectation with respect to zeta minus 1 of the payoff applied to the Euler discretization. All right. So before stating the theorem, we needed to have two assumptions. So the first assumption, basically, it's related to the boundness of the derivative. So here we assume that for any p, there exists positive random variables such that the piece derivative of the Euler. So the piece derivative of the Euler discretization with respect to the different Euler increments. Let me go back so you can connect. So here you see that we defined, I mean, the Euler increments as such. So what I'm saying is that the piece derivative of the Euler discretization with respect to L1 up to LP Euler increments is bounded by a positive random variables which have finite moments for any n. Okay, so this is what we assume. Now, is this assumption natural or not? Yes, it's fulfilled, I mean, for many problems, because this requires that the diffusion coefficient is smooth. So if you have that condition, then you guarantee that this assumption is valid. Now, a more stronger assumption that we introduced is the following. So here we assume that for any p, we have that the inverse of the derivative of the Euler discretization with respect to y, here y denotes the coarsest variable, to the power minus p is bounded. So here, just let me we introduce this notation. I mean, for to simplify, I mean the presentation. So when I introduce this, I mean that if Fn is of p hat of Gn, means that there is a random variable with finite moments of all orders for any n. Okay. So this assumption is stronger than the first one, but also we motivated some sufficient conditions such that it is valid. And basically, the sufficient conditions were related to the derivative, the first derivative of the diffusion coefficients. And we showed that, I mean, this can be satisfied by some models. For instance, if you take one-dimensional models with linear and constant diffusions, or you take multivariate models with linear drift and constant diffusion, and then you can connect also to multivariate log normal model motivated by an earlier work of Christian and co-authors. I should note that even though you may have cases that the assumption is not valid, the method can still work. And this can be seen if you take your terminal value of the process is Wt squared. So this is the Brownian motion at capital time T squared. Then basically your problem will be reduced to having, I mean, the integrand evaluated at the coarsest random variables. And then, I mean, you don't have to, you don't introduce any other random variables that you need to satisfy the condition with respect to. Okay, so given these two assumptions, now we are able to introduce the theorem. So what the theorem says is that assume that you have the Euler discretization that we have defined before, and we satisfy the two assumptions. Then for any p and any indices from n1 to np and k1 up to kp, such that kj is between 0 and 2 to the power nj, the function hn. So let me first remind you about the function hn, which is here the expectation with respect to the coarsest random variable of our quantity of interest. So the function hn have p derivative with respect to the variables zeta n1 k1 up to zeta np kp that are bounded in the sense that we have introduced before. Okay, I should note here that the constant that appears here will increase with respect to p, but also they will increase with respect to n, which is the number of time steps. And this basically motivated that in practice we use the Richardson extrapolation, because in the case that you can end up with an analytic function, you expect that the analyticity region will shrink as n grows. So you can improve the problem by considering Richardson extrapolation, because this will get you a better control on the weak rate with fewer number of time steps. Any question regarding the theorem and its assumptions? Okay. All right. So I will not go through the whole proof, but I will just show a sketch of the proof. So the basic idea is to apply successfully the technique of dividing by the derivative of the Euler discretization with respect to the coarsest variable, and then integrate by part. Okay. So what we do is that, let's say that you start with a modified version G delta of your initial pay of G that was discontinuous. And you define also the corresponding modified Hn. So the first thing is that we prove that we can interchange the integration and differentiation. So this is the first step that you do here. And then what you do is that you multiply and divide by this term, as I explained before. And then what you end up with is the following term. And the idea basically is to transfer the derivative that you have here to this term. Okay, so this is what you do by integration by part. And given the assumption, you see here that this includes this term, which basically related to the assumption too. So you need to control the growth of those derivatives. And also the assumption one basically is related, I mean, to this term. So what we do is that we could transfer the derivative that was in the modifier version to the terms that are in the right-hand side, and then you can get rid of the modification. So this can be applied to your initially discontinuous pair of J. Okay, so this is the sketch of the proof. Any question related to that? Okay. All right, so how to combine the numerical smoothing with the different techniques? So the first thing that I want to stress is that you still need, I mean, even though you gain in terms of regularity, you need still to apply, as I said, Richardson extrapolation, because remember, so I mean, remember that your resulting problem will scale in dimension with respect to the number of time steps. So you have interest to control the weak error with Richardson extrapolation because we will need fewer time steps compared to the case you don't use that. Yeah. So, and here we use the same technique that we did for another work that we did for rough volatility mode. Okay. Now let's discuss the error that we end up when we combine the numerical smoothing with adaptive sparse grids. So let's define, I mean, the adaptive sparse grids estimator as such. So basically, you can see that you have three contributions of error. So the first one basically comes from discretization or the weak error. And since here we are using Euler, Mayama, it's O delta t. I mean, if you use another scheme, it will be delta t to the power alpha. The second contribution is what we call the numerical smoothing error. And I mean, if you see this, the smoothing, the numerical smoothing procedure, you can see that this is involved. Yeah, so this involves two kinds of errors. So the root finding error and also the numerical pre-integration, so the quadrature error. And that's why you see, oops. And that's why you see here that in the estimates that we provide, so this is a contribution that comes from the quadrature error with respect to the number of Laguerre quadrature points. And this will be related to the error coming from the root find. And the last contribution is basically the adaptive sparse grid quadrature error. As we have shown, it will have the following rate of convergence. Okay. Now, to get an optimal performance of the adaptive sparse grids, basically you want to minimize the work. I mean, here the work basically will be of order the number of the quadrature points used in adaptive sparse grids times the number of quadrature Laguerre points for the numerical pre-integration times the number of time steps. And you want to minimize this subject that your total error fulfills a certain tolerance. And what we have shown is that in the best scenario, where P and S are very large compared to 1, so S basically, let me remind what is S and P. So S will be related to the order of derivative of G with respect to Y1 that are bounded, okay? And P basically is related to the mixed differences of the integrand I that we end up with. And this can be connected to the smoothness theorem that I showed before. So since we end up with a C infinity function, then you expect P to be large. Okay, so we have shown that the work of adaptive sparse grids in this optimal scenario will be of order 12 to the power -1. And you can see that this is much better than the work of Monte Carlo in its best case scenario. So if you have large regularity orders S and P, then you end up with much better complexity for adaptive sparse grids compared to Monte Carlo. Now for the multi-level estimator, I'll just go back to the idea that we did for the numerical smoothing, and what we do is that for each level of the multi-level estimator, we compute, I mean, this quantity for each level L, but here remember that the random variables that were used here will be different in each level. So that's why I introduced this notation, but also this will be computed with the step size delta TL, but also with the number of quadrature points at level L and Newton tolerance at level L. So this is the notation that I will use. And what we show basically is that thanks to the regularity that we obtained by this numerical smoothing, first we improve the rate of the Vance decay, which now is of order delta T compared to delta TL to the power 1/2. This leads that we get the complexity if we have a Lipschitz function initially, which was not the case, compared to 12 to the power minus 2.5 initially without any smoothing. And the last thing that we showed is that we now have more control on the kurtosis, which is of order O1, so it's bounded, compared to a growth that is of order delta TL to the power minus 1/2, if we don't do any smoothing. Now, as we did with adaptive sparse grids, also the same discussion applies here. These two will not change. The only change is that now you take, the bias with respect to the finest level of the multi-level Monte Carlo. That's why here we have delta TL. The same happened for the numerical smoothing. So the parameters here will be, the error will be evaluated at the finest level. And what changes basically is that instead of the quadrature error, you end up now with the statistical error of the multi-level estimator. And we show that it has the following structure with respect to the parameters, the number of Laguerre points and the Newton tolerance. And here we sum up over the total levels of the multi-level estimator. Any question? Okay, sorry. Any question regarding the error discussion? Yeah.
Yeah. How does this numerical smoothing compare to, for example, an analytical smoothing, like say, if you use a modified indicator function or something? What is the disadvantage of using that?
Yeah, as I specified. So there is two kinds of modification. You have bias-free modification if you have a certain knowledge of good subset of random variables where you condition with respect to which, and then you end up with expectation, like, I can come back. Yeah, so this, you have two ways. So if you have no bias introduced by conditioning with respect to a certain subset of random variables using, a la Romani 2Z tool, if you have that possibility, this is the first thing that you do. Don't complicate your life. But there are cases where it's not obvious, which random variables that, it's good to condition with, and if you end up with a good regularity of the required regularity, because also the quasi-Monte Carlo require less regularity. The multi-level requires only Lipschicity, maybe. The quasi-Monte Carlo requires a control on the weighted mixed first derivatives, but the adaptive sparse grids require much more. So it depends also how much you want in terms of regularity. But also you can do modification by convoluting with some kernels, but this has an error that could scale exponential with dimension. So what we are suggesting is something complementary. So there is no good way or bad way in the absolute sense. Each way has advantages and disadvantages, and depending on the problem, you may use the thing that is more suitable to your problem. Does it answer your question?
Yes, yes. Thank you.
Okay, thank you. Okay, so let me go to the numerical examples. All right, so in this example, I consider the Heston model, the digital option under the Heston model. And what we show here is the quadrature, only the last contribution. So the quadrature error with respect to the adaptive, this, let me go back. So, yeah. So I'm showing basically this error. So the convergence of this error, the last contribution. So what we see here is that if you don't do any smoothing, basically there is no convergence. And you see that you gain much more better behavior with respect to the number of quadrature points used by adaptive sparse grids if you smooth out your problem. And you see also, this is the second plot when you use Richardson extrapolation. So maybe I did not say it before, but here when I did the analysis of the error, I assumed I don't do any Richardson extrapolation, because if I use Richardson extrapolation, this will help to control better the weak error because you have a higher order convergence, and then this will reduce the number of dimension, and you expect that the behavior of the quadrature will be much better because dimension is always problematic. Okay, you alleviate the problem by creating some anisotropy, but still, there are some order of dimension that will hurt you, and you see here that the advantage of applying Richardson extrapolation, and in both cases you see that they really compares good. If you don't do any smoothing. Okay, and this is what, this is dimension 16, because here it's a 1D Heston, but you have 2 to the times n, I mean the dimension, because you have 2 SDEs. So this is 16 dimension, and you see that smoothing really helps a lot. Okay, how this affects the quasi-Monte Carlo. And here we consider 2 examples. The first one is digital under Heston, and the second one digital under GBM. And you see basically that without smoothing, you get the worst rate, which is 1/2. And you see that, I mean, by doing this numerical smoothing, you get much better rate. I mean, that is close to 1. I mean, this is maybe a numerical artifact, but maybe if you go asymptotically, I mean, you can get even the optimal rate. The same observation holds for the digital option under the GBM model. So consistently, we have seen that the numerical smoothing also improves the performance of the quasi-Monte Carlo method. Now, okay, we are doing some operation, which is numerical smoothing, but is it costly or not? And in that sense, here we look at the cost of each. So we have 2 errors. I mean, two operations on numerical smoothing. We have the root finding, and we have the quadrature, the 1D quadrature, Laguerre quadrature. So here you see, in some sense, the effect, I mean, of the number of quadrature points used for the numerical pre-integration. And you see, and here I'm showing the relative smoothing error by fixing. So I'm overkilling the Newton tolerance to just see the effect of the pre-integration. And you see that with few points less than 10, I mean, you can get a relative error below 1%. And even, I mean, even with something around 16, you can get something, I mean, for the 10⁻⁴ in relative sense. And the same observation holds here for the error coming from the Newton iteration. So you see, I mean, even starting with very coarse tolerance for the Newton, you get something that is in relative sense 10⁻⁴, and you don't gain too much by going very deep in the terms of the Newton tolerance. So this tells you that the numerical smoothing procedure is very cheap that we are introducing, but we get very good regularity as a consequence of that. Okay. Also, we compare the performance of adaptive sparse grids with respect to the Monte Carlo. And what you okay, here I'm comparing with different configuration with and without using Richardson extrapolation. And what you can notice is that if you take a relative error that is something below 1%, let's say, you see that you require maybe a CPU time of order 10, and you require 30 times more if you use Monte Carlo with or without Richardson extrapolation. So this is a big deal. And we see here for different examples that, I mean, what we saw is that you get something between 10 and 100 times faster around dimension, let's say around 20, than the Monte Carlo. So here what we do is that we fix a relative error that is below 1%, and we try to see the gain that we got with respect to the Monte Carlo estimator. So this is the different examples that we test. Okay. Now let's see how the numerical smoothing affects the multi-level estimator. So what we observed first is that we hugely, screen. Okay. So so what we observed is that we hugely decrease, I mean, the kurtosis at the finest level for the different examples. So the digital option and the GBM and Heston, and also we have bounded kurtosis when estimating densities. And we observe consistently that we improved the variance decay rate from 1/2 to 1 when using numerical smoothing. And this has an impact on the complexity. So you get order of tall -2 up to logarithmic term compared to tall to the power -2.5. And the same complexity was observed when we tried to estimate densities if you consider GBM or Heston dynamics. Now let's see one illustration. So here I'm showing you a digital option under Heston. So you see that if you look at the variance decay, you get a rate that is of order 1/2. And you see that the kurtosis is exploding with the rate delta TL to the power -1/2 if you don't do any smoothing. And you can see that this improves a lot when you do the numerical smoothing. So now you get a rate of decay that is of order 1. Moreover, you get a control on the kurtosis, which even decreases, and it stays bounded for deeper levels. Also, this relates to the complexity. So you see, I mean, that if you compare the multi-level with numerical smoothing, which are the blue curve here, you get much better complexity, which is tall minus 2 up to logarithmic term, compared to the green, to the red curve, which scales tall to the power minus 2.5. So this is also was for the digital option case under Hest. Okay, so to conclude, so we have introduced this numerical smoothing idea. Again, can be seen as a complementary idea to the different options that you have depending on what you want to do and the regularity that you want to acquire in your problem. And we showed how to combine with adapt sparse gates and quasi-Monte Carlo. We did some analysis about the regularity of the smoothed integral. And we show that by combining it with sparse gates quasi-Monte Carlo, we outperform the Monte Carlo method for different cases. Another nice observation, which I did not tell you, is that in the case of the Heston model, maybe, okay, we still have time, so. Yeah. So if you observe, I mean, in the case of the Heston model, you have the square root of the variance. If you use classical numerical schemes like truncation, fixed Euler, or moment matching schemes, you may, basically you may end up with a low regularity of the paths that you have. And what we observed is that this affects even, the sparse gate quadrature. So what we used a sum of Ornstein-Uhlenbeck processes to approximate, those variances. So this is, in some sense, the last observation for that work, and further details can be seen on that manuscript. Now, in the context of the multi-level, we also extended this to further cases, including density estimations, and we showed, how we control now better the kurtosis. We improve the decay of the variance, which implies a better complexities than the case without any smoothing. Again, I highlight here, we don't need to use higher order schemes because this comes with a penalty of cost and also coupling and also kurtosis. Again, there was a work that used this to estimate density, but what one expects is that the strong converse behavior can deteriorate for the limiting case, and also you have a bias that can scale exponentially with respect to the dimension, something that we don't have. Yeah, and this approach can be extended to different applications. This is something that we try to follow up, such that other model dynamics and payoff structure like barrier options, or even autocallables, or something that is more sophisticated. Also, one can use it for computing financial risk, computing distribution functions, and also for risk estimation purposes. And further details can be seen in these references. And these are the related works to my talk. And thank you.
So questions? Thank you, Chiheb, first for the nice talk.
Thanks for the nice talk. Just one more question. Can one sort of optimize over how many variables you're doing the pre-integration in? Because if I understand right, I think you're doing the pre-integration in one variable, right?
Yes.
Is that something that can be optimized? Like maybe you can do, I don't know.
So, okay. So this is related to phi. Okay. So first, as I showed, you can have the generic case where you can have multiple roots, but you can guarantee that you have only one root. If we specify this in the paper. So if you have monotonicities, for instance, condition on phi, and a condition on the growth, like for the second derivatives, for instance, or the behavior at the limit, then you can ensure that you have either simple root or you have no roots even. So this is basically relates, to this phi. Yeah. This phi that happens, combined with the non-smooth functions in your payoff. But this is, I would say that also this is problem dependent. Depending on your quantity of interest, you can know, if you have one root, or you can have how many roots that you can end up with. So it can be treated case by case.
Okay. Okay. Thanks again for the nice talk. Yeah.
More questions? I have a small question. So, are there cases where you don't have? I mean, it's difficult to localize this discontinuity. I mean, so you have a priori knowledge where the discontinuity is, right?
I mean, again, so what we introduce here is the first stage of the numerical smoothing. I mean, I cannot say that this can be extended to any case. As I said, I mean, we have different applications. For instance, I mean, so let me go back. So if you consider, for instance, I mean, distribution functions, this can be easily, I mean, given some dynamics, this is contribution of two things, the dynamics and also the payoff structure. So, okay, I cannot say that, I mean, there are no cases where it's hard, I mean, to localize the thing. The takeaway is the following. So you have different techniques. Whenever you cannot use the like bias-free methods or simple methods to get, I mean, better regularity, and you ensure, as I explained, depends how much you want as regularity, then you can go to numerical smoothing if it's easy, because at the end, I mean, what you want to localize is, okay, so go back, sorry. So when I specified the root finding, so let me, yeah. So basically, this is related, I mean, to solving this problem, right? The phi at x bar, and express it, I mean, in terms of these random variables to be equal to 0. So you look at your problem. If the structure of your phi is something that you can understand and you can easily compute, I mean, the root finding, then, I mean, this is the way to go. But there could be problems. I mean, maybe it's not the suitable way. So it's not kind of for any setting. Yeah.
Okay, thank you. More questions? Okay, if not, let us thank again Chiheb for this nice talk. Now we have to move quickly to the library. Yeah?